I'm going to go ahead and introduce our next speaker, Ashley Rao. Ashley is a licensed architect with Lears Weinzimfeld Associates of Boston. She is the project manager for the celebrated and successful Adohi Hall project at the University of Arkansas. This is a 708-bed, 202,000 square foot dormitory complex under construction in Fayetteville, Arkansas. Currently the largest dormitory project in the U.S. to be constructed using advanced timber technology. Ashley, as always, we're thrilled to have you, and we're looking very forward to your presentation. So, Ashley?
Bruce, I'm so happy to be here. Thank you for having me as part of this panel today. I am here to talk about the designer's role in anticipating and addressing construction hurdles. A brief introduction, I am with Lears Weinzimfeld Associates. We're a Boston-based architectural practice, nationally recognized for design excellence. Although we've been known typically for our work in academic infrastructure, community and civic buildings, we're increasingly known for our work in mass timber, including the John W. Oliver Design Building at UMass, the University of Massachusetts Amherst, that was, at the time it was built in 2017, the largest academic building in mass timber. Today, I'm going to focus on, as a case study, Adohi Hall at the University of Arkansas. At 202,000 square feet, it's the largest mass timber project in the United States, and it represents a pioneering use of CLT in student housing. I know we've heard about other student housing projects today, but this one was one of the earliest forays into that field. It was completed a year ago in August 2019. And just a quick thank you. I was the project manager on this project, so I saw it from the very beginning to the end, but this was a complex project that would not have been possible without many, many talented people working on it. And especially today, I just want to mention the construction manager, Nabholz Construction, the mass timber supplier, Bender Holtz Holtzpack, and the structural engineer, Equilibrium. To take you back to the beginning, this project was a new residence hall housing 700 students that was at a remove from the main core of the University of Arkansas campus in an area that was adjacent both to Athletic Valley, these large athletic facilities here, and the Oak Ridge Trail, a restored native landscape running through campus. Our design concept was really to regreen the site from the inside and the outside to create a sustainable student housing project in a preserved and recreated woodland, and to highlight the expressive potential of wood throughout as much as possible. Zooming in on the site plan, the serpentine building form really creates and defines 3 courtyard locations that are connected underneath the building bridges above. The ground floor houses major social and academic spaces. Building C is the cabin area, social area, and these are a series of performance and academic spaces. But a lot of the building decisions were driven by the typical student residential floor plan up above. So you see here the really kind of regular grid of student residence modules and lots of bathrooms, which is important to remember as we get forward in this. The structural grid here, the mass timber framework, was glulam beams and columns and CLT floor and roof slabs. And I just mentioned here, and this is, you may recognize the WoodWorks carbon summary, but one of the most important reasons that we were doing this, that we were considering mass timber for this project, was really the way the environmental impact of using a low embodied carbon and carbon sequestering material was an important strategy for the University of Arkansas's sustainability goals. In this aerial view, you see the 2 buildings, building A to the north, L-shaped, and building B to the south, C-shaped, that are linked. They're each 5 stories tall, and they're linked in the middle by this 1-story cabin with the major social spaces. It's worth noting there was significant topography on this site, a 25-foot change from the north to the south, that kind of fed into some of the construction logistics as well. So, since I'm the architect on this panel, I have to show you some of the pretty pictures. These are the completed project. So here you have the view from Stadium Drive that passes to the east of the complex. And as I said before, celebrating wood was really a key design goal. So what we're really proud of here was the ability to expose structural timber as much as possible and marry that with locally sourced finished wood. At the street level, you're seeing exposed glulam trusses and columns here in the cabin social space. You're seeing the exposed CLT ceilings in the residential floors above, and you're seeing exposed locally sourced Arkansas cypress that creates the finished soffit and highlights points of entry. Here again at the central courtyard, looking into the cabin space, you're seeing that wood on display as a major design element. And during the day as well. So just again to point out what you're seeing here, this is glulam columns, glulam beams and trusses. This is exposed CLT slab here on the edges, combined with Arkansas cypress used as finished material on the walls and as a wood grill in the ceiling to conceal the major mechanical spaces. Moving on down the site through the project, a series of major academic spaces cascade down the hill. This is a performance space. And one thing that I'll come back to this later, but we actually were able to use some of the salvaged CLT, so really a CLT skid that's a delivery system for glulam and CLT, and recreate that into custom furniture on the site. So these bench tops here are actually salvaged CLT through the process. And here in the woodshop area, that same CLT skid was used to create custom tables that were part of the workshop space. Again, one thing that we're really proud of here was we have beautiful exposed columns and beams and a really pristine CLT slab up above that we worked really hard to keep this clean so we could expose it in the major public areas. And in the student residential spaces above, again, the intent was to have wood and natural materials exposed in every room. So with that kind of as background, I wanted to take you back in the project and share some strategies that we use to anticipate construction hurdles. There's really 5 key takeaways here. Some of the things that made this project successful were that we created a shared foundation of knowledge, that we made cost-effective design choices, that we evaluated code issues early, and considered species and fabricator differences, and leveraged the prefabrication potential of mass timber. So I wanted to start with this. One of the most impactful early steps on this project was to create a shared foundation of knowledge through a site visit that included mass timber building precedents and actually visiting CLT fabrication sites in person. And this group of people you're seeing moving through here includes the design team, but it also includes key decision makers in terms of the client side, the University of Arkansas Housing and University of Arkansas Architecture Department, as well as the CM itself. So this is really bringing everybody together to understand what some of the challenges and potentials of this fabrication method might mean. So then making cost-effective design choices. The client really initiated the mass timber interest on this project, but we were trying to create a design that was cost-effective and that could be realizable in either steel or wood. So we developed the structure on parallel tracks through schematic design with cost estimates really at every phase to compare conventional steel concrete construction to mass timber construction. One of the key decisions in making mass timber cost effective here was looking carefully at the student room and together with the overall structural module. So looking here and thinking about the typical 8-foot by 40-foot CLT panel available in North America, we really worked back and forth between program and structural module to make sure that we were creating kind of cost-effective decisions at every point that satisfied the program as well. So moving here from the typical student room to the typical residential wing, where again, you're seeing that, you're seeing how that resolves into an 8x40 CLT panel, how we're able to effectively use that modular dimension, minimizing waste and kind of maximizing the structural potential of that. Another key strategy was to evaluate a wide range of structural frameworks. So you're kind of illustrating and honing down on where the optimal choices are in mass timber. So we examined mass timber with a variety of core and shear wall structures and compared that to steel. And what you're seeing here is that the residential wing that we developed took advantage of structural efficiencies in mass timber with one-way beams as opposed to a two-way steel structure with composite deck. So there were some efficiencies to be found there. Another key takeaway was to evaluate code issues early. So we met early and often with the university and state fire marshals beginning in pre-design. And this project would be a pioneering use of mass timber in the state for a student residence hall. And we wanted to make sure that everyone was on board with and understood, and that all concerns were kind of vetted early in the process. So the local fire marshal made it clear that they would not entertain any variances for this project, which ended up influencing key decisions around construction type and concealed spaces. Again, we used the kind of comparing to conventional structure back and forth to help drive decisions and illustrate points about construction type. Here, the massing, the area, and the desired room count led us towards a 5-story building. We illustrated what that would look like in a steel frame building, type 2A, protected non-combustible construction, 1-hour fire-rated structural frame, and then compared that kind of apples to apples with an advanced timber frame building, type 3B, non-combustible exterior walls, but unprotected combustible structural frame, floors, ceilings, and roof. One question that frequently comes up here is, why not type 4? Isn't that the natural fit for mass timber? But again, we understood that the client, the university, did not want to expose mechanical systems in student areas for reasons of protection and longevity and maintenance. So we knew that there would be some drop ceilings and concealed ceilings in these spaces. So again, we were looking for construction types that would allow that flexibility. Early conceptual details, again, identified key code issues, such as the separation of a combustible structure from a non-combustible exterior, and understanding how a glulam column can form part of a rated partition, and how that non-combustible exterior enclosure meets that rated partition. And so again, this is very early in the pre-design phase, but just to try to identify as much as possible any of those issues that would need further vetting. At the end of schematic design, the client made the decision to continue in mass timber. And at about 50% CD, the mass timber package was awarded early. Binderholz and Holzpack won the contract, and this kicked off a design assist phase to fully detail the timber and coordinate with the specifics of their wood products. This is an important phase because there were several critical changes that needed to be understood and addressed. A key takeaway is the importance of considering species and fabricator differences as you're making your kind of final selections. Among the key differences that this design assist phase really unearthed were differences in the typical member size. So the basis of design was a Doug fir glulam beam, 14¼ inches wide and 18 inches deep. The basis of construction beam was a spruce pine fir glulam, again 14¼ inches wide, but 20½ inches deep. And this was largely due in differences in species strength and European versus North American standards. And so you say, okay, 2½ inches, is that a big deal? And in most cases, no, but in one very specific instance, this was a big deal. There was a key pitch point that happened in each of the typical student rooms. You're seeing kind of a reflected ceiling plan mechanical diagram on your right, and an axon of the typical student room on your left. And the key issue here is there's one point where a supply duct needed to dive underneath the glulam beam in order to kind of feed the student wall here. So that was the one place where we were most constrained in overall ceiling height. And that was the one place where this 2½ inches really was a major issue. So the compromise solution was choosing a beam that was a little bit fatter, understanding, as Greg just highlighted, that might have some cost implications there, but was significantly less deep so that we could continue with the kind of existing mechanical system and that coordination and avoid any negative impact on the ceiling height that would really, ripple through all of the student rooms. Another decision was the issue of factory installed cast beam hangers versus field installed beam hangers. So our basis of design had originally called for factory installed beam hangers with tight fitting male-female sliding or Sherpa connections. And given the size of the project, Binderholz had recommended substituting a bearing bracket that you're seeing here for interior connections and a tight fitting pin connection for perimeter connections. These connectors are both field installed, but do allow for greater adjustability, which ended up being important on a project of this size. So ultimately, I think this field adjustment was important, but there was a significant addition to the field labor associated with the change, which I think, again, A big room that can help you vet through all the implications of those decisions is really a key part of the communication process. The fabricator had also recommended substituting multi-story columns up to 40 feet long in lieu of the single-story columns that the design had originally specified. And this change represented a savings in overall material and also in kind of effort of installation, fewer connections, but required a thoughtful redetailing of the column to floor connection to ensure that, number one, the fire separation between floors was maintained. It was just a 30-minute separation. And two, to protect the continuous column from the moisture of the wet pour gypcrete topping that was on top of each CLT slab. The last piece here was that the design assist phase was an opportunity to leverage the prefabrication potential of mass timber. Think back to all of those student bathrooms, one bathroom for every double student room, and how that kind of ripples through the entire project. So there was a combined effort to coordinate and factory drill all CLT penetrations, and that really involved the design team, it involved the CM, and it involved the fabricator. We were reconciling the design model, the contractor's coordination model, and the fabricator's production model, trying to make sure that we all had all the holes throughout the project in the same place. So there were 4,113 penetrations in total. The CM called it the Swiss cheese slab. But the key point here is that each penetration was located, coordinated, reviewed for clash detection, and cored in the factory before the timber was delivered to the site. Looking forward in time, these pre-drilled penetrations led to a lot of time savings in the actual installation of the plumbing. It expedited the installation, the plumbing, the mechanical systems in the field. But this coordination process did require more input from the overall design team at a key point in time than in conventional construction. So I think one of the takeaways here is just thinking of that coordination process and thinking of all the people who need to be involved for it to be effective and to build that into the schedule from the onset. So as much as I would love to say that we successfully anticipated all the construction hurdles at Adobe, we did not. I wanted to highlight some key lessons from the field about addressing construction hurdles as they arise during the process of construction. So the key takeaways here are really about protecting exposed structure, accommodating field tolerances, and addressing necessary field modifications. Going back to the timeline, with the early release of the timber package, the timber fabrication transport overlapped with early site work and concrete work in the field. And you're really seeing that here in this aerial that shows the overall construction sequence, which moved from the south to the north of the site. It allowed sector by sector assembly of the mass timber and piggybacking of trades. But you see kind of before all that, these concrete cores that were the key shear cores preceded the entire timber installation. This is a photo from the in-progress timber installation of the first wing. And a key lesson here was protect exposed structure, especially when that structure is moisture and light sensitive and will be exposed as a finished material. Both the CLT and the glulam arrived wrapped from the factory, and our initial guidance had been to leave those factory wrap protections in place as much as possible during assembly in order to, to preserve that protection layer that was already there. However, what we found in the field was that columns are being partially unwrapped in order to install connector brackets, leading to uneven discoloration due to UV light exposure, up and down the height of the column. At the ground floor, we actually found that some of these factory wrappings were actually collecting water, accumulating water at the base of them here, as you see in this inset picture. So with these issues in mind, and in consultation with the CM, we reversed course and recommended that each timber element be unwrapped at installation. And just noting here, the contractor team also installed bump protection around the ground floor columns to protect them from equipment damage during construction. So our site visits highlighted the importance of craft and consistency And we typically ended each site visit with a quick huddle with the CM, with the timber installer and the design team to highlight and discuss emerging issues that we were seeing kind of in real time. One of the site visits kind of caught this issue. I know that we spoke about it earlier, but the importance of, again, sealing against water protecting all of these joints. You're seeing here both the kind of spline joint and again, that key column to slab joint. So just making sure that all of those really were watertight, that we were protecting from water on the slab above, and again, protecting from that wet gypcrete pour. Another key issue was accommodating field tolerances. And I know this is not the first time you've heard about that today. But again, in this case study, while the timber was on the ocean, the contractor team performed a field survey of the cast in place concrete cores, which as you can see were already erected here. And what they found is that a couple of them were off by as much as 1 3/4 inches from top to bottom, which was well beyond the anticipated tolerance. And again, this is an issue where you have really highly precisely fabricated timber and cast in place concrete and really kind of dealing with some of the joints between those. So we called a joint brainstorming session to try and address the solution and create something that was workable in the field, and leverage the timber construction process and was going to have an aesthetically pleasing result. So working with the mass timber fabricator and the contractor, the team created a field adjustment manual to adjust this specific condition. Whereas you can see here, the glulam beam is meeting a concrete core through a kind of steel fitting assembly. So in the typical connection, you have 3/8 of an inch gap between the concrete core and the glulam beam, and no gap between the concrete core and this custom steel bracket. However, if the concrete opens, if the concrete is pulling away from that, basically we needed to find a way to shim that and to manage those within the tolerance of each piece of this connection. If the concrete core closed, if it was leaning basically toward the beam, then the steel bracket had to be cut. And this was just, again, a simple step-by-step manual of what needed to be addressed, what was okay, and have this vetted by everyone throughout the entire process. Ultimately, what we decided to do was that for future wings, we would not pre-drill these pin connections as the glulam beam met the concrete core, and instead created a field drill jig so that this could really be adjusted on site to address each of these unique conditions and the unique field tolerances of the concrete core. Again, this was more site labor, but this built in some adjustability that we really needed at that point in time. And finally, the multi-story column span had a couple of unintended consequences that, again, we just needed to work through all together as a team. As you can see here, one issue was there was some needed bracing. You have these 40-foot tall columns. They're out there until you kind of get the slabs in place and the beams in place to brace them. So that was one thing that we just had to make sure was consistently applied throughout the entire project. The other was looking at this corner slab detail right here. Made perfect sense. Right here where you're seeing this is the pink CLT slab. It's notched to go around the multi-story columns. There's going to be a filler piece in here, but there's going to be a filler piece in here. In actuality, this was totally impossible to erect in the field, to thread the CLT slab over a 40-foot tall column, basically to sink it in, because you have your tolerances going in different directions here. So the installer field cut the corner off the CLT slab, as you can see here, in order to actually erect it in place. But from a design perspective, we needed that corner. We needed it, it was finished ceiling in that student room, and it was also support for the exterior enclosure. So the solution was ultimately inserting an L-shaped piece of CLT with a custom bracket that was either mounted to steel or or mounted to the glulam column in some cases. And again, this was an exposed slab that we were hoping to keep clean, but it was not in highly visible locations. So ultimately it was, I think, not a perfect solution, but one that just addressed the reality of the situation on the ground. So this is a brief construction video taken from the north of the entire process of construction. So you're seeing first the concrete work, the core is going up, foundations being poured. And then mass timber arriving, the southernmost wing. And I think it's really interesting for us to see how quickly those go up. And you can see actually in the end, we're doing building A and building B at the same time with two different crews that are really putting that all together. And that takes us to the end. Oops, sorry. Thank you so much for having me. I look forward to the questions as part of the panel discussion.